Okay, so in this lecture we are going to work out the differential equation corresponding to Legendre polynomials. So like we said, in our development of the theory of orthogonal polynomials, we started with this abstract formulation, worked out the polynomials, and then we have treated the differential equation corresponding to the polynomial as sort of a property of the polynomial, right? But many times it's the treatment is carried out in the opposite direction, which is you start with the differential equation and then you work out solutions to the differential equation, and you argue that certain kinds of parameters will give you polynomials, and then you get the polynomials and you work out the properties. But in this lecture we will see how we can get the differential equation corresponding to Legendre polynomials using the standard prescription we have given out. Okay, so the idea is to look for this this quantity, work out this quantity and see, and we have already argued that this must be a factor of the polynomial in question. So you must construct this product of these three quantities for the Legendre polynomials. W of x is equal to 1, s of x is equal to x squared minus 1. So if you put x squared minus 1 and then multiply by the derivative of this Legendre polynomial of nth order Pn of x, and then take the derivative of this object. So this whole quantity better be directly proportional to the polynomial itself. And so basically we have to work out this constant lambda, this coefficient needs to be determined, and that we will do with the use of Rodrigues formula and a rule which goes by the name of Leibniz rule, which is basically an application of the binomial theorem. So let's see what the Leibniz rule is. So the Leibniz rule is useful if you want to take the nth derivative of a product of two functions. We know that the derivative of the product of two functions is given by the product of of the derivative of one function and leaving the other as a constant, plus the product of the derivative of the other function leaving the first one as a constant, right? So if you want to take the nth derivative of product, it turns out that there is this binomial like formula available. So you have summation over r going from 0 to n choose r, the rth derivative of the first function u times the n minus rth derivative of the second function v with respect to x, right? So this is in fact a direct consequence of the binomial theorem. And so one way to see this is to write this derivative d that we want to carry as du plus dv, right? So in other words, so if you want to operate this on some function uv, we know that this is going to be basically du plus dv acting on uv. What this notation really means is you treat so when du acts on uv, it will treat v as a constant. So you write it, it's basically like saying v times dou v by dou x. Well, I mean, we don't even need let's go back to this. So we don't so we write it as v times du by dx plus u times dv by dx, right? So we don't even need partial derivatives. So basically you can introduce this notation, and good notation automatically leads you to this result. So basically what we are interested in finding is du plus dv the whole power n acting on some product of two functions, and then you use the binomial theorem to expand it out, and you can verify that indeed the binomial theorem which is being applied to the sum of two operators will give you this relation, right? So you can check this by considering increasing powers of n, for example, and see for yourself that indeed it holds out. Basically the idea is quite simple, and we will use this this rule, right? So we start with the Rodrigues formula for Legendre polynomials, which is just 1 over 2 to the n factorial times the nth derivative of x squared minus 1 the whole power n. And now we define this function v of x to be x squared minus 1 the whole power n. Now suppose we take the derivative of this function, dv by dx is n times x squared minus 1 the whole power n minus 1. So now it's convenient to multiply this derivative by x squared minus 1 so that you basically get back this v itself, right? So you have x squared minus 1 times dv by dx will be just, there is going to be this extra factor 2 times n times x times v of x, right? So this n times x squared minus 1 to the n minus 1, then you have also 2x, you collect all this that and write it as 2nx, but then since you have also multiplied by x squared minus 1, you have filled back the lost power, and so you get back v of x, right? So now we can differentiate this this equality n plus 1 times, right? So that using the Leibniz rule. So now if we do this, the left hand side is, you think of this is a product of two functions, x squared minus 1 is your u and dv by dx is like your v in this formula that we wrote down. And so we might think that if you're going to take a derivative with n plus 1 times, we might have actually terms ranging from r equal to 0 all the way up to n plus 1, so n plus 2 terms we might think, but it turns out that in this case there are only 3 terms which survive. The reason is because we have a quadratic function here. One of these terms is a quadratic function whose zero derivative is x squared minus 1, then there's a first derivative which will be 2x, and then the second derivative is 2, but any higher order derivatives are going to just give you 0, so all those extra terms will cancel. So the first term is when you don't take a derivative of this at all, that's going to be x squared minus 1 times the n plus 1th derivative of dv by dx, which is nothing but the n plus 2th derivative of v, plus then we have this coefficient, the binomial coefficient, which is n plus 1 choose 1, which is just n plus 1, then 2x from this first term, then the n plus 1th, so the nth derivative of dv by dx, which is n plus 1th derivative of v. Then we have the next term is going to be n plus 1 choose 2, which is n plus 1 into n divided by 2 times 2 comes from the second derivative of this function, and then we must take the n minus 1th derivative of this function, which is just the nth derivative of v. So the left hand side is done. So the n plus 1 derivative of the left hand side gives us 3 terms, and the n plus 1 derivative of the right hand side gives us only 2 terms. So because we have just a linear function, just x is one of them and the other one is v. So the first term is when you don't take a derivative with respect to x, but all the derivative is entirely borne by v. So that gives us 2n times x times n plus 1th derivative of v. Then we have plus 2n times n plus 1 choose 1. So derivative of x is just 1. So then you have to take nth derivative of v. So just there are these 2 terms on the right hand side. So both on the left hand side and the right hand side, the result has been obtained by applying the Leibniz rule. So you should check this and convince yourself that it indeed is correct. So now we simplify this. We see that there is this term for n plus 2th derivative, then n plus 1th derivative. Here we have n plus 1 times 2x, and then we also have 2n x. So they can be simplified to just give you 2x times n plus 1 derivative of v with respect to x. Then this must be equal to, this stuff can go to the right hand side. So 2n into n plus 1 minus so this 2 has also been cancelled here, so minus n into n plus 1, so it's just n times n plus 1 times the nth derivative of v on the right hand side. So now, we recall that what is v? V of x is after all x squared minus 1 the whole power n, which is really, so if you take the nth derivative of v, it's really nothing but the Legendre polynomial itself, except that there is this extra factor. So let's rewrite the nth derivative of v as 2 to the n times n factorial times Pn of x, and then plug this back in. So we see that then you have to take one extra derivative here and 2 extra derivatives here, and so this factor remains unchanged when you take this derivative of v or second derivative of v. So all of that will just get cancelled on both sides, and so effectively you're just left with this equation x squared minus 1 times d squared Pn of x divided by dx squared plus 2x times the first derivative of Pn of x with respect to x is equal to n times n plus 1 times Pn of x. So now this can of course be rewritten as d by dx of x squared minus 1 times dPn of x divided by dx equal to the right hand side as it is. So a moment of a moment's thought here reveals that this is really the same form that we already started with. We wanted to work out this, and so in fact we have obtained our lambda. So the lambda here corresponding to the nth polynomial is actually just n times n plus 1, right? So this is, you can think of this as like an eigenvalue equation. So there is this operation, you operate with this stuff on Pn, we will get back some eigenvalue times the same eigenfunction, right? And so only if you choose your lambda to be of this form, n into n plus 1, where n is an integer, only then do you get polynomials, and those polynomials are the Legendre polynomials. So the differential equation satisfied by Legendre polynomials is exactly this, where it's important that this n into n plus 1 both appears, and where n is an integer, right? So this is we have worked out this differential equation, which perhaps we are all familiar with, because whenever there is spherical symmetry, and as is the case in a lot of problems in E&M and quantum mechanics, this differential equation does appear. And so there you start with this differential equation where this constraint is not necessarily already put in, and then we argue that if we want solutions which are polynomial, so that the wave function has a physically viable meaning associated with it, then we are interested in getting these Legendre polynomials which turn out to be Legendre polynomials, and then often that's the starting point from which we make a thorough study of these polynomials and their properties. Okay, so but in this lecture we have started with the Legendre polynomials, used some of their properties, and used this general prescription to work out the differential equation corresponding to Legendre polynomials. Thank you.